Good evening. We're back for the fourth and final video on process control charts, one of the 7 quality tools, probably one of the most important ones. And if you haven't watched the videos leading up to this, I did a series of 3 videos right before this that shows how to construct a control chart, the subtle differences between types of charts, and we even plotted a few. Tonight, we're going to really draw the value out of this quality tool by interpreting these charts. Now, just a quick review, we talked about 2 different types of charts. There's many types, but the X bar and the R chart are just probably 2 of the most common types. The X bar, of course, is where you take the average of your subgroup. We were talking about a subgroups of 3. N is the symbol for subgroup or sample size. So we're talking about an N equals 3. So on an X bar chart, we take the average or the arithmetic mean of the 3 samples, and then we plot that as a single point. That's just one type of control chart. The other type we talked about was the range, where even using the same n equals 3, you take the max minus the min, and that equals the range. And it's probably the simplest measurement of variation within a sample. Similarly, you take that range and you plot it on a control chart. So take a look at those previous 3 videos and you can get up to speed on this. So tonight, again, we're going to look at the interpretation of these control charts. Let's take a look at this first control chart we have here. The pink represents the plot of our data, and we have an upper and lower specification limit, and then of course the calculated upper and lower control limits. So the first thing we see here, even right here, here's one, and I think here's one too. Anytime a point, even a single point, goes out of control, or we should say outside the control limits, we'll call that an out of control situation. So it can just be 1 point. We're going to look at some more of that later. But what you'll start noticing as you look at a lot of these control charts is you'll start noticing patterns. Okay, so let's take a look at this. First of all, we have some random variation: 1 up, 1 down, 1 up, down, and it's near, maybe slightly below, but it's near the nominal or the center line. And then something happens here, it jumps. Now take a look at this. Again, we already know a couple of those points go out, but within that range, though, it's actually fairly narrow. And then we see it jumps back down again to another narrow process range. So this area right here, and kind of the trend we're looking at right here is jumps in data. Okay, so there's a number of reasons why this might happen, but as a quality engineer or technician, if you're investigating the situation, the first thing I would look at is say, okay, what happened between here and here and here and here? As we know, the horizontal axis is usually time or some similar independent variable. So let's just say this is maybe it's a typical manufacturing operation, and every hour we have the operator drawing samples. I would look at the 5th hour of the shift. Maybe there was a maintenance issue. Maybe this happens all the time too, where maybe this is day shift, and then the new guy comes in. I hate to blame afternoon shift all the time, but afternoon shift, and he sees something, or he likes running a different spot, so there could be a shift in operators. Maybe this is a sub-assembly operation, and you have non-homogeneous data. In other words, this isn't a continuous flow of data, but this might be one batch of material, and then this is a second batch of material that processes differently. You see that in, for instance, plastic injection molding. You see that in forging, all sorts of applications where maybe the raw material shifted and that wasn't noted on the chart. So this could be a shift in operators, a shift in raw material, or some other change maybe in the machine, that sort of thing. So anyway, when we see, as I mentioned in previous videos, when we see a process go out of control, the next step is investigate. So there's some information on your run chart, on your control chart, to help you start that investigation. Okay, so let's take a look at another one. That's jumps. Now let's take a look at this one. This is similar, but actually subtly different. We see our lines plotted, and none of them are out. Maybe they're touching, but we'll say they're not out, or maybe they're even just slightly out. But there's a very narrow process range. It's just that the whole process has shifted. Okay, that's what we call a shift. Now, this could be due to a number of factors as well. Certainly raw material coming in. I already mentioned plastics injection molding or plastics extrusion. You typically purchase resin, plastic resin, the raw material for those processes in large master batches. And you can see some variation from master batch to master batch, and maybe in the melt flow index, for instance. If you're familiar with those processes, you'll know what I'm talking about. But there'll be a shift. Maybe if you're in steel, maybe hot rolling or forging, you can see differences in chemistry or something. So the whole raw material has shifted. So the process itself stayed the same, but maybe the raw material coming in shifted, or vice versa. You know, there could have been a engineering change of some sort. But anyway, this is a shift up. Could be a shift down, but the reason it's a shift is because the variation is still very narrow, but it's no longer centered. Again, next step, investigate. This is just a short amount of data, but if I were investigating this process, I would go back some time to where I saw that the process was in control, and we'll say roughly centered within the control limits. So this is a shift. Okay, let's take a look at another one here. Again, these are patterns. Patterns help you. These are shortcuts to seeing. When you see these types of patterns, they're clues about what might be going on in the process. Okay, now let's take a look at this one. So this at first looks like a trend. We're going to talk about trends in a little bit, but then it comes back down, and again, if you ever have a point outside the control limits, automatically it's out of control. But even if these hadn't gone outside the control limits, what you see here is a longer term. We call this a recurring pattern. So there's something going on in the process that produces variable results, but it takes longer for that to occur than the sampling size. You know, this might be, again, this might be the hours of a shift, and each one of these represents an hour, but there could be some changes over 8, 10, 20 hours that are producing this variation. The most obvious thought on that is ambient conditions. And again, thinking back to factory work, if you work in a place with 3 shifts, you could have cold nights, you could have hot during the day, and it produces different results depending on your process. Humidity, other environmental factors. Sometimes you see longer term shifts within the process itself, not related to ambient conditions, and it could be the turning on or off of, like, we'll just say systems within your plant. Maybe it's not the machine itself, but maybe it's the air compressor, or maybe it's your water cooling system, something facilities related. I've seen situations in factories where during the day there was a high usage of the air compressors, so you had a lower pressure throughout the plant. So then maybe afternoon shift comes in, it's just a skeleton crew. Well, all of a sudden the shop air pressure goes up, and that can affect your process. That could be a recurring, or that could be a jump too. But anyway, just keep that in mind and look for these longer patterns of change. Okay, so let's take a look at this next one here, and I put a couple different types. Okay. And generally, let's take a look at this first. Okay, first of all, obviously the points are well within the upper and lower spec limits, well within the upper and lower control limits, and there's just like, gosh, it's barely even moving. It's at nominal. You think, well, what's the problem here? I mean, that seems like the perfect process. Well, maybe it is, maybe it isn't. Okay, so when I look at this process, I generally call this a lack of variability. And again, if you look back, let me spell this out here. Okay, if you look back at our previous lectures, we talked about how we came up with these upper and lower control limits, and they pretty much represent the full statistical span of the process. So if your process is not using up the whole span or not even anywhere close to it, it tells me something. It tells me that there's been a shift. Maybe it's a positive shift. Again, it doesn't always mean it's a bad thing when you see a pattern. In fact, in a scenario like this, maybe the engineering department had a process improvement, I don't know, Kaizen event or something, and actually narrowed the variability in the process. Well, these control limits maybe were based on a previous state of the process when it had wider variability. So this could indicate a process improvement and might trigger the need for calculating new control limits. Okay, so it's not necessarily a bad thing. It just means that this isn't reflective of the process as it was designed with these control limits. Okay, let's take a look at this one. What do we got going on here? This is a lack of variability too, but it's kind of special. You know, it's like right there, and then it goes down, down. You know, it seems like it's almost discrete data. In other words, it's only moving through certain increments instead of being continuous. Now, you know, again, could be a lot of reasons for this, but one of the first things I would look at if I saw this was the gauging. Because maybe the gauging that's measuring this is lacking the resolution, or we might call it this discrimination necessary to plot a good values on this chart. Okay, the idea of the chart is basically continuous data. Let's just say, I don't know, I'd have to make this up. Let's just say these are thousandths of an inch, or we'll just say 10 thousandths of an inch or whatever. But the gauge you're using is only capable of measuring whatever, maybe every 20 thousandths or every 5 thousandths. So you're not getting, there's no chance of even getting a value in between these. So the gauge lacks discrimination and therefore isn't giving you as helpful of results as you might need. Sometimes you see gauges, maybe the chart was set up for, we'll say calipers with 2 places of resolution, and for some reason this person's only using calipers with 1 place of resolution. So some of the precision gets boxed out. So here's another example, could be the same thing, but again, when I see a straight line all the way across here, I mean, something's wrong. You know, it could be an improvement. It's probably something operator related, you know. It could be the gauging, could be a combination of the two, but something weird's going on there. It shouldn't, your data should not be a straight line. Okay, it might, you know, have 0 variability, but trust me, that is probably not an accurate representation of your process. So any of these conditions are worth looking into. Okay, so let's move on. Let's take another look here. This is, this is something you've just seen. If you do this for long enough, and I've done this for quite a long time, you start seeing patterns like this. I brought this out as a subset. You don't even see this in a lot of textbooks, but this is another version of lack of variability. So let's just take a look here. We have some down, down, and then look, it flattens out, up, down, up. It looks like it's random, down, and then flattens out. Maybe it's a recurring pattern, right? Maybe it's a shift, but for some reason, between here and here, right at our lower control limit, it suddenly flattens out, okay? In other words, it lacks variability, but only in certain spots. And again, this is just experience speaking, but this could be truncated data, okay? Now, we already know in a SPC environment, you know, when a process goes out of control, you investigate. Sometimes you shut down and investigate. It depends what your process is and what the rules of your shop are. But maybe there's an operator who doesn't really want to shut the machine down, maybe in an incentive-based system, or for whatever reason, they don't want to shut down, they don't want to investigate. They may just truncate, or in other words, stop measuring parts below a certain limit, and then it comes back. So if you ever see the lack of variability at a control limit, could be truncated data. So take a look at it that way. Okay, and now this is probably, this is a very common pattern. You see this very often in analyzing process control charts, SPC charts. So what do we have here? We have some randomness, down, up, and then up, and then up, and up, and up, and up, and then bang, then it goes out, okay? This is a trend failure, very common. Tool wear, machine wear, those two are probably the most common. If this is an X bar chart, if this is a range chart, again, this could be a range chart as well. If your R bar value, your average range, oh, I'm sorry, if your, I apologize, if your R, your range of each subgroup is going up and up and up, it could be some vibration in the system, a belt is loose, something is causing a greater amount of variation, some sort of vibration or wobble or something like that in the system. An X bar chart, where you're measuring the average of the subgroups and it's trending up, I usually look for tool wear, you know, again, thinking back to injection molding or extrusion, plastics extrusion, you got material passing over that die over and over again, and the die wears as the plastic keeps pushing past, so maybe we're measuring the outside diameter with this chart, and it's going to get bigger and bigger and bigger as the tool wears, and then eventually it goes out of control. So tool wear, machine wear, that type of stuff, if this is an X bar chart, and then just some source of variation, vibration or a misalignment of some sort if this is a range chart. Okay, so let's take a look at this last chart here, and let's see what we have here. We're looking at all the points. They're certainly within the upper and lower spec limit. They're within the upper lower control limit. I see a nice amount of randomness, up, down, you know. I see that it's roughly centered throughout or within the control limit ranges, and I have some up near the high limit and some near the low limit. Well, this isn't out of control at all. This is actually in control. So this is, if your calculated control limits are representative of the process, it's probably going to look something like this. This is good news. Your process is in control. It's performing as designed and as it was performing when you calculated the control limits. Okay, so this is the interpretation of process control charts. This is really where the rubber meets the road, and that this quality tool becomes most useful.